Hi Chase, I wanted to take a moment and summarize what we had studied at your house on Sunday night and try to clarify some things, and if nothing else, present it to you in a way that it's more compact. The first thing that we talked about was the first derivative test, and that determines critical points where the slope of f of x is equal to 0. With that, once we know what these points are where the slope is equal to 0, we can then look to see whether or not these are maximums or minimums. Remember that if they give you a closed interval, which is to say that these points over here, that it ends at some point right here, it's a closed interval is what they call it, and over here, that when we look for maximums and minimums, we not only have to look at these points, but we also need to consider the endpoints, because like in this case, this one value, even though the derivative is not equal to 0, it's actually going to be greater than this local maximum right here. So remember that what the critical points, if f of x is equal to 0, we either have a maximum, a minimum, or a saddle point, and we'll talk more about these. So I'm actually going to flip the camera here, so don't get like super nauseous and throw up. All right, so if the first thing that we do to find critical points is we check to see where the derivative, which is the slope of the line f of x at any given point, is equal to 0. So right up here, you can note that right here, a slope is equal to 0 because it's flat. A slope is equal to 0 here because it's also flat. So those are the points where f of x is equal to 0. Now, once we've determined that a point is equal to 0, we then need to look at if the sign of the first derivative goes from being positive to on the other side of the critical point of it being negative. And if that's the case, that is going to tell us that this is a maximum like this. If you can think about my hand right here sitting on that curve, and if we go here, we see that the derivative here is positive, right? It then goes to 0 right here, and then it goes negative down here. And so in that case, when it goes from positive to negative, you then have a local maximum right there. Here's just another diagram that I sketched out. Additionally, when it goes from being negative to positive, then what you know is that your critical point here is a minimum right here. So in this case right here, we're seeing the derivative go from negative to positive. So here's your slope right here, it's definitely negative. It goes to 0 and then it starts to go up. The slope starts to go up. And so in that case, when the first derivative goes from negative to positive, you have a minimum right here. Now, if the first derivative test goes to 0 and the sign is unchanged, then the critical point is what's called a saddle point right here. And that means that you come down your curve right here, and it's negative, it goes to 0, and then it continues on being negative, or it's positive, 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 goes to 0, and then continues on positive. If that happens, then it's known as a saddle point, which is different than a point of inflection. A saddle point is actually a special case of a point of inflection, and that's what we're going to talk about next, because that is tied into the second derivative test. And the second derivative test confirms that you have a maximum when f double prime is less than 0, or a minimum when f double prime is greater than 0. Remember that when we take another derivative, like in this case we took a derivative of the first derivative, that gives us the second derivative, we're essentially looking for where or how the first derivative is changing. So remember that was the first derivatives of the slopes of the line, and we're asking ourselves, are those slopes getting smaller, smaller, in which case f double prime is less than 0, that means that you have a maximum. Or is the second derivative greater than 0, in which case you have a minimum. And I've tried to sketch some of that out here. You can see that in the first drawing that I had over to the right, that the f double prime of some point x naught that we've sketched there, that it's decreasing, or that it's less than 0. And what that means now is that your original derivative, f prime of x, was decreasing. So these arrows right here were getting smaller, their slope was getting smaller, 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 right? And that's how you know that that's going to have a second derivative that's less than 0. On the next one over here, we have the opposite. We can see from our plot here that this is going to be a local minimum. And if we plugged in the second derivative here, we would see that this is greater than 0. The second derivative across this whole domain here is going to be greater than 0. And what that means for f prime, remember f prime is just the slope of the function f of x, right? F prime is going to be increasing over this area. And so let's look to see if we can do it with kind of the arrow here. Here you can see it's negative, it's 0, and now the slope is positive. So it went from negative to 0 to a positive number, which means that your derivative over this area is increasing. It went from negative to 0 to positive. Now, in addition, there's something called concavity in the points of inflection. And so concavity is determined when f double prime of x is less than 0, like in this case. That means that your function is concave down, right? On the other side, if you can have a function where the second derivative is positive, then you know that this is concave upward right here. In addition, you have something that's called a point of inflection. Now, I talked about how the saddle point, which was down here, is actually just a special case of the point of inflection, which is over here. So the point of inflection means that you've switched now from being concave up, right, or actually being concave down, right, where your first derivative was changing and it was getting smaller. You hit this point, and then you start to see your second derivative actually increase. And this could be flipped the other way, where at first your second derivative is greater than 0, and then finally your second derivative on this side would be less than 0. So you can flip that graph. But the point is, for an inflection point, you have the second derivative changing sign around some point, x0, that you're looking at. A saddle point is a special case because in the saddle point, where your second derivative changes from, in this case, being negative, in this case, it changes from concave downward, concave upward to concave downward, or downward to upward. The inflection point is also at a point where f prime of x is equal to 0. And so that's what gives you kind of this familiar saddle point. A classic example of a saddle point is f of x equals x cubed. Anyway, I hope that this kind of helps you here, what I've laid out, and it's hopefully clearer than what I was able to present to you on, I think maybe Wednesday night we were working. Anyway, good luck with your studies, and hopefully we can chat soon.